My name is Daniel Gates, and I will be talking about the bomb calorimeter experiment, which was experiment number 4. So our objective with this experiment was to become more familiar with how a bomb calorimeter works, to test out the principles, try loading it, determine thermal capacitance of the calorimeter, and find heat values for whatever fuel we were using, and then given fuel. So this is our basic apparatus. You've got the outer shell here. This is, you can see it over there. It's a big bucket. And then inside there's a steel canister. And this steel canister right here on this little tray holds the fuel. So the fuel is loaded in there with a little wire. And then this canister is vacuumed to remove the air, and then oxygen is pumped in. And this is done several times to make sure that there's pure oxygen inside the calorimeter. And then it's submerged in the water. This right here circulates the water to make sure that as much of the water as possible comes in contact with the canister to allow heat transfer to occur more easily. And then basically these leads are thermocouple leads, or this is a thermocouple, and that measures the temperature of the water as combustion happens. So once the canister is inserted and the calorimeter is sealed, it's ignited, and then the contents of the canister are combusted fully, and the temperature is recorded. And from the recorded temperature, you can discover the heat output from combustion of the given fuel based on the thermal capacitance of the system, which is why we had to solve for that using a substance of known heat value, which would be benzoic acid tablet. So you can see here a close-up of the canister with the valves, pressure relief valves, electrode terminals, and this wire right here we actually had to manually insert, and it was measured to be a length of wire that contained around 23 calories of energy, because part of that was burned off during combustion, and that had to be subtracted from the calorie output. So right here you can see the data for the temperature versus time for both the benzoic acid and our fuel, which was a peanut. And as you can see, the temperature starts off rapidly increasing from steady state once it starts combusting, and it plateaus at a certain temperature once combustion is finished. And it took a similar amount of time to fully combust. The peanut had a slightly bigger temperature change than the benzoic acid tablet. So our equations for this lab were as follows. From the first law, you get these two equations for the Q, which is the heat value, or heat of combustion, and MCV, which is thermal capacitance. So for the calorimeter, the thermal capacitance would be Q. To get the thermal capacitance of the calorimeter, you would use the known value of heat of combustion for the benzoic acid in this equation right here, with the temperature change to find the thermal capacitance of the calorimeter itself, which is the amount of energy it would take to increase the temperature of the system by 1 degree Kelvin. Heat of combustion of the fuel sample after that can be calculated using the calorimeter's thermal capacitance and the recorded temperature change. So for the calorimeter's thermal capacitance, using these values, I got from the internet 6,318 calories for a gram of benzoic acid. And then there's an additional 10 calories of wire burned away. So using that and the temperature change, which was 2.32 Kelvin, we got a thermal capacitance of 2,866 calories per Kelvin. Using that value, we found the heating value of the peanut, which was 7,185.7 calories after removing the 8 calories that were burned away from the wire in that run. So from the package, a serving size of peanuts was 160 kilocalories, and it was about 28 peanuts per serving. So the calculated calories per peanut from that was 5,329.8 calories, so we were about 35% off from what the package estimated. But that can change based on the size of the individual peanut, how much salt was on it, how much moisture was on it. So other fuel sources, one of the other groups used Funyuns as their fuel source, and they got 5,359.4 calories per gram, so that was a lot closer to the benzoic acid tablet. it contained less calories than the peanut. I don't know what size onion they used. I guess it was a small piece because I had to fit in the tray. But as you can see here, gasoline has around 11,300 calories per gram. Diesel is 10,700. Propane has 11,900. So you can see the fuel sources generally have a lot more heat of combustion than food, because I guess that's why they're used as fuel sources. So yeah, any questions?
Yeah, so why do you attribute, how do you attribute the 34% change between your data and the package data?
I think for the package it would be like an average calculated using, I think they used an ounce, or it was about a fourth a cup of peanuts. So if they got, say, a bunch of smaller peanuts or a bunch of larger peanuts, or if we had a particularly large or small one, that would change the value. As well as any water that we got in the canister during the loading could affect that. Or if there are any combustion products left from the benzoic acid tablet, that could also eventually change the value.
Any other questions? Okay, thank you.